Alright, next we're going to talk about section 2.3, calculating limits using the limit laws. So we're going to introduce limit laws, and then we're going to have a strategy as to how to actually proceed by evaluating limits at the end of this section. Instead of just guessing in the previous section, now we're going to have a set of rules and then a way of exactly knowing what to do when we have a limit question. So limit laws. Suppose that C is a constant and the limit as x goes to a f of x exists. The limit as x goes to a of g of x exists. Then the first law, if you're doing the limit as x goes to a of f of x plus or minus g of x, it's the limit of f of x plus the limit of g of x plus or minus. So if you're doing the limit of the sum, then you can find the limit individually and then add or subtract your limit answers. Same thing with constant. If you have a constant times f of x and you want to find the limit, you pull the constant out and then you do the limit of f of x. You would still get the same answer. And if you have the product of two functions and you want to find the limit, you can find the limit of each function and then times their limits times the limit of g of x. Of course, all x goes to a, x goes to a. Same thing with the quotient, as long as you don't divide by 0. Limit as x goes to a of f over g is the limit of f of x over the limit of g of x as x goes to a, as long as you don't divide by 0. Okay, so as an example, page 102, number 2, it says the graphs of f and g are given, use them to evaluate the limit. So you need to be looking at the graphs, and we're talking about number 2, page 102. So if you want to find the limit of f of x plus g of x, looking at the graph as x goes to 2, part A, well, if you look at the graphs right here, so if you look at f of x, limit as x goes to 2, it's -1, and g of x as x goes to 2, it's 2, so we're going to add -1 plus 2. Okay, so this is the limit as x goes to 2 f of x plus limit as x goes to 2 g of x. Remember, this is -1 and this is 2, so -1 plus 2 is 1, and so on. If you want to do a limit of f times g, limit of f times g, it's limit of f of x times limit of g of x. I'm just not putting the x goes to 2 to save work, which is -1 times 2, which is -2. Okay, so for D you divide. For f, let's do f just a little different. What's f of -1 plus limit as x goes to -1 of g of x. Well, f of -1 from the, you can look at the graph, f of -1 is 3, and limit of g of x as x goes to -1, as x goes to -1, it's 2. 3 plus 2 is 5. Okay, so now rule number 5. So remember we went over rules 1, 2, 3, 4. By the way, all these rules are posted on a handout in your notes. Okay, they're right here. Properties of limits handout. So you can check that out. Okay, properties of limit handout. It's all in there. And then on the back of this handout, strategy to evaluate limit, which I'm going to go over shortly. So we've gone over 4 rules of limits. The 5th one is the limit as x goes to a of f of x to the power n. So if you're doing the limit of a power, you can do the limit of the function inside the parentheses and then raise it to the power, as long as that limit exists and n is a positive number. Okay, n is a positive number, and the limit of a constant is the constant itself, and the limit of x as x goes to a is a. So basically you plug it in, and when you have a constant, like for this one, if f of x equals c, this is c, then as x goes to 1 or 2 or 3 or 4 or -1, the y value is always c. That's why. Number 8, the limit as x goes to a of x to the n is a to the n. Again, you plug it in, where n is positive integer. And the limit of the nth root of a of x, number 9, the limit as x goes to a of the nth root of x, again you plug it in, as long as it's defined and real. Okay, as long as this is defined and a real number, which means a has to be positive when n is even. And number 10, the limit as x goes to a of the nth root. See, we did the nth root of x. Now any f of x, as long as it's defined of real, it's going to be the nth root of the limit as x goes to a f of x, as long as it's defined and real. Okay, so let's see several examples about this. Limit as u goes to -2, square root of u to the 4 plus 3u minus 6 or plus 6. So remember, this is exactly this rule, so you plug it in, so you're gonna get, so basically you're doing this, the limit as u goes to -2 of u4 plus 3u plus 6, so which would be -2 to the 4 is 16, 3 times -2 is -6, plus 6, which is square root of 16, which is 4. Also, if you're doing the limit as t goes to 2 of t squared minus 2 over t squared minus 3t plus 5 squared, again this is f of t to a power, so you do the limit of what's on the inside, so you plug it in basically. That's 4 minus 2, 4 minus 6 plus 5 squared, which is 4 over 9. Pretty straightforward. And we're getting to the general properties now. Direct substitution. Property. So if f is a polynomial function, or a rational function. See, when we say rational function, it's a fraction of two polynomials. Then the limit as x goes to a, f of x equals f of a. So you just plug it in, basically, direct substitution. If a is in the domain of f, of course, if a is in the domain of f. So let's look at several examples. What's the limit as x goes to 1 of the polynomial function? You just plug it in. Minus 4 times 1 squared plus 3, which cancels. Now the limit as x goes to root 2, x to the 4 plus x squared over x squared minus 4, a rational function, a fraction of two polynomials. So again, we plug it in, so we get root 2 to the 4 plus root 2 squared over root 2 squared minus 4, which would be 4 plus 2 over 2 minus 4, which is negative 3. Now for number 3, the limit as x goes to 2, x squared minus 4 over x minus 2. If you plug it in, you get 4 minus 4 over 2 minus 2. Now, there's a way for doing this, which actually has a rule, but let me explain what you need to do. So if you can reduce the fraction, limit as x goes to 2, x minus 2, x plus 2, we can cancel x minus 2 because x does not equal 2, x is approaching 2. And remember, approaching 2 from the left and approaching 2 from the right doesn't equal 2. It's like 1.9, 2.1, 1.99, 2.01. So we can cancel out. We're not dividing by 0. Limit as x goes to 2 of x plus 2, you plug it in, you get 4. And there's the, so this has a theorem. This is a result. Let's talk about it right now. Theorem: if f of x equals g of x, where x is not a, then the limit as x goes to a, f of x equals the limit as x goes to a, g of x, provided that limit exists. So let's explain this with the example that we just did. So this is f of x, and this is g of x. Okay, f of x is x squared minus 4 over x minus 2, and g of x is x plus 2. So f of x is x squared minus 4 over x minus 2, and g of x is x plus 2. Remember, we got this by factoring, where x is not 2. Remember, x is approaching 2, but it doesn't equal 2. We cannot divide by x minus 2 unless we make sure that x is not 2. We cannot divide by 0. Okay? Then the limit of x squared minus 4 over x minus 2 equals the limit of x plus 2, provided the limit exists, which it does exist because it equals 4. Okay. So basically, if you're doing the limit of a rational function and you get 0 over 0, and if you can reduce it, and then do the limit, and that's going to be the answer. Number 14, page 103. The limit as x goes to negative 3, x squared plus 3x over x squared minus x minus 12. So if we plug negative 3 in there, and then negative 3 squared minus negative 3 minus 12. So this is 9 minus 9 is 0. This is 9 plus 9. 9 plus 3 is 12. 12 minus 12 is 0. But we can actually reduce this by writing this as x times x plus 3. And this is x minus 3. X plus 4. Or x plus 3, x minus 4. We can cancel this out. So we get what we call g of x. So this would be the limit as x goes to negative 3 of g of x, which is x over x minus 4. If we plug it in now, which is 3 over 7. Okay, here's another example. It might get a little bit more complicated. Limit as h goes to 0 of 2 plus h cubed minus 8 over h. So if we plug it in, we get 8 minus 8 and then 0. So this is not exactly as simple as the previous one. So what we're going to do, we're going to work this out. 2 plus h cubed is going to equal, so the limit as h goes to 0, it's going to be, if you either FOIL it or use the binomial theorem, it would be, you can do 2 plus h, 2 plus h, 2 plus h, which would be 4 plus 4h plus h squared times 2 plus h, and then if you work this out, it's going to be 8 plus 12h plus 6h squared plus h cubed, and then this minus 8. And look what happens now, the 8's cancel out. We can factor out an h from top. All this to cancel out the h at the bottom, and then we can do the limit. Well, look what we do the limit now. When we plug the 0 in, it will be 12 plus 0 plus 0, so that limit does equal 12. Okay, another example. Again, I'm trying to give you a variety of different kinds of problems, okay? So hopefully that would help on the test. The limit as u goes to 2 of square root of 4u plus 1 minus 3 over u minus 2. So when we put a 2 in there, we get 8 plus 1 is 9, that's a 3 minus 3 is 0, and then 2 minus 2 is 0. See, when we have a square root like this with two terms and we can't factor that, so what we're going to do is we're going to rationalize it. And rationalize the numerator means you times by the conjugate, and the conjugate means you switch the sign. So you do 4u plus 1 plus 3, and then 4u plus 1 plus 3. Okay, and then you FOIL it. So you leave the bottom, you don't mess with this. 4u plus 1 plus 3. Okay, if you FOIL the top, you get 4u plus 1 minus 9, so it's 4u minus 8, which is 4 times u minus 2. So that's the top. The bottom is u minus 2, and hopefully you can see what's going on now. Limit as u goes to 2. In case I lost u, so I times by the conjugate of the numerator. Conjugate means you switch the sign. I FOIL the top. Square root of 4u plus 1 times square root of 4u plus 1 is 4u plus 1. Outer and inner will cancel out. And then negative 3 times 3 is negative 9. 1 minus 9 is 8. Factored out the 4 and got the numerator. And the bottom I brought down. Now you know what's going to happen. Cancel this out. And then plug in the 2. So you get 4 over root 4u plus 1 plus 3, which would be 2/3 if you plug the 2 in. Let's look at 52 from page 104. So if you let f of x equals the piecewise defined function x squared Come on. F of x equals x squared plus 1 if x is less than 1, and it's x minus 2 squared if x is greater or equal to 1. Part A, what's the limit as x goes to 1 from the left of f of x? So obviously 1 from the left, meaning it's less than 1, like 0.9, 0.9999999, so less than 1 right here, so we're going to plug it in there. So 1 squared plus 1 is 2. What's the limit as x goes to 1 from the right? 1 from the right is greater than 1. So that's right there. If you plug 1 in there, 1 minus 2 squared, negative 1 squared is 1. Now, does the limit as x goes to 1 f of x, does it exist? This does not exist. Why it doesn't exist? Since the left limit and the right limit don't equal. Since the limit as x goes to 1 from the left does not equal the limit as x goes to 1 from. Remember, this is one of the cases where the limit may not exist, although the left limit exists and the right limit exists, but they don't equal. If the left limit exists and the right limit exists and they equal, then the limit exists and it equals that common value. Okay. Evaluate part A, the limit as x goes to 2 from the left, absolute value of x minus 2 over x minus 2. Now remember, x goes to 2 from the left, meaning x is less than 2, and if you put a 2 in there you get 0 over 0, okay? And we cannot factor that, so we gotta get rid of the absolute value, and we know absolute value of a is a if a is greater or equal to 0, and it's the opposite of a if a is less than 0. A in this case is x minus 2. Now if x is less than 2, like 1.9 minus 2 is negative, so a is negative, so the absolute value is going to be the opposite of a, so the absolute value of x minus 2 is the opposite of x minus 2, and that's what we're going to put in there. Limit as x goes to 2 from the left, opposite of x minus 2 over x minus 2, which is negative 1. Negative 1 over 1 is negative 1. Now, so when you have absolute value, you're either going to get exactly the same or the opposite, depending on whether what's inside the absolute value is positive or negative. So for example, if I'm doing same thing, but instead of 2 minus, it's 2 plus. Absolute value of x minus 2 over x minus 2. 2 plus, that means x is greater than 2, like 2.1, 2.2, whatever, just greater than 2. So any number you put greater than 2 in here for x, minus 2 is positive. So that means we're in this case, so the absolute value of anything is itself. So we'll drop the absolute value. We don't put a negative because it's positive, and the answer is 1. Part C, what's the limit as x goes to 2? Absolute value of x minus 2 over x minus 2. Why it does not exist? Because a doesn't equal b. In a we got negative 1, in b we got 1, so it doesn't exist. Okay. Another example, part A, what's the limit as x goes to 5 from the left of the greatest integer in x? Well, this is the greatest integer less than or equal to x. So for example, if you look at the number line, 3, negative 3. So the greatest integer of 3.1 is 3. Why? Because you want the closest integer to 3.1 from the left. The greatest integer of 3, since 3 is an integer because it says less or equal to x, so it's 3. And then say the greatest integer of 3.2 is 3. The greatest integer of, say, negative 1.5 is negative 2. It's not negative 1. You always look to the left, less or equal. Your calculator has this key. I'm sure you're gonna like this. You go to math, and it's under numbers, and then it's number 4, int. Say greatest integer of negative 1.5. It's negative 2. Okay. So if you put a 5 minus there, so that's like 4.9, 4.99. So 4.9, 4.99. So the greatest integer is 4. So if you want to do, say, the limit as x goes to 5 from the right of the greatest integer in x. Again, this is 5.1, 5.2, so it's going to be 5. Okay, check that out. Finally, the squeeze, or what we call the sandwich theorem, squeeze or sandwich theorem. If you cannot find the limit of a function, and this function is squeezed between two other functions whose limits are known, if g of x is between f of x and h of x, where x is near a and the limit as x goes to a, f of x equals L, the limit as x goes to a of h of x equals L, then the limit as x goes to a of g of x equals L. So if this goes to L and this goes to L, then g of x is greater or equal to L and less or equal to L, so it must equal to L. We're talking limit wise. And an example about this, number 40, page 103. If 2x is less or equal to g of x is less or equal x4 minus x squared plus 2. You see, we don't know what g of x is for all x. Then what's the limit of g of x? Well, 2x is gonna go to 2. We're doing limit as x goes to 1 of 2x. It's 2. And this is gonna go to 1 minus 1 plus 2 is 2. So g of x must go to 2. Okay, as simple as that. Now, how do we evaluate limits since we know so many things about limits? Here's the handout that I want to go over with you. Okay, strategy for evaluating limits. So the first thing you do is you plug the number in first. If you get an answer, you're done. Okay, so just plug and chop. Okay. If you get 0 over 0, we saw an example about, you factor and reduce. If it doesn't factor, you rationalize the numerator. We saw an example about that. And then you always want a graph to confirm your result. If all of the above fails, then this is something we're going to talk about later on, limit of sin x over x and so on. Okay? And that's it for today.